Hi everyone. We've been working with polynomials and breaking them apart into pieces. First we had some that we could factor, then we learned about how to divide different expressions out to make it smaller till we got down to a quadratic and then could factor it or use the quadratic formula or whatever. What we're going to do is take it a step further. What happens if we're given a polynomial? We need to break it up into pieces, but we can't factor it. It's not factorable in any method that we know how. And I'm not given an expression that I can divide out. So what would I do? And that's what I'm going to show you today. Where would I even begin to break this apart into pieces? So what the method that you would use is to synthetic division, because that's the way to go. Use synthetic division. But there are only some numbers that will work. So you're going to actually have to hunt and peck with synthetic division until you find factors with this method, which sounds nightmarish. But there's only certain numbers that'll work, so you can eliminate a whole bunch right off the bat. And the way to do that is to look at two key numbers. One is the constant at the end. This number is very, very important. All the zeros of this polynomial have to go into 5 evenly. They have to be a factor of 5. So the numbers to pick are factors of 5, which in this case would just be 1 or 5. But the other thing is this coefficient, this leading coefficient, can also get in the way as well. And that tends to complicate things a little bit. So here's the formula for finding all the possible numbers. You take the factors of your constant here at the end, the factors of the constant. So what you do is you take the factors of the constant over the factors of the leading coefficient and both signs, positive and negative. So our factors of our constant are 1 and 5. So the numerator can be a 1 or a 5. And the factors of our leading coefficient are 1 and 2, so that's over 1 and 2. So here are the possibles, positive or negative. So I'm just going to do it this way so I don't have to write positive and negative each one. So 1 over 1 and 5 over 1, so positive or negative 1 or 5, or 1 over 2, 5 over 2, positive or negative 1/2, or 5 over 2. Those are the only possible things you can check. Now, if we want to set up a synthetic division, we have a place to start. We're not just picking numbers at random. We're going to pick only the possible ones first. So let me actually show you how you would do this. It sounds really hard, but it isn't that bad, especially when you get fast at synthetic division. But we had plus or minus 1, plus or minus 5, plus or minus 1/2, or plus or minus 5 over 2, right? So let's start with the easy. Let's start with 1. Let's do that. So bring down the 2 and let's do this. Multiply, add, multiply, add, multiply, and 1 didn't work. So, okay, if you're using a whiteboard, not a problem. Erase that, write again. If you're using paper, do it in pencil lightly. It's okay. Now just try -1. So put a negative here. And now do it again. So I brought down my 2. Multiply, add, multiply, add, multiply. Awesome. So we found our first 0 is -1. That's awesome. And this, now we're down because this was an x cubed. That means this is 2x squared minus 3x plus 5. Now we could use, if we have to find all the zeros, now we can either factor, and 10, we might be able to factor this. Positive 10, no, we can't factor this. So we'd have to use a quadratic formula to see if there's other. If they ask just for the real ones, we might be done. The other two might be imaginary, I don't know. But that's how we do it. Okay, this particular problem asks only for the rational roots. So it doesn't ask for all the zeros. By the way, roots are the same as zeros, are the same as solutions. They'll ask it in different ways, but it's the same thing. So we're still looking for the zeros. So we're going to look for factors of 8 over factors of 3. So 1, 2, 4, and 8, 1/3, 2/3, 4/3, and 8/3. Positive and negative, those are our choices. It's always easier to start with 1. So set up synthetic and go through it, and I'll show you. Now I'll tell you right off the bat, because I have access to the book, and this is the problem in your example problem. This is the got it question. The only rational zero is a fraction. But you wouldn't know that until you worked through this. So let me work through a couple just to show you how fast it can be. So let's start with 1. So this is 3, 10, 10, 16. We know right away that's not going to work. So -1. -3, 4, -4, 2. Nope, that doesn't work. So the next one is 2. 6, 13, 26. Oh my goodness, that definitely doesn't work. So let's try -2. -6, 1, -2, 4, -8. That is so much closer, but it doesn't work. That would be -16. It almost makes you think, did I make a mistake? But I didn't. Now I'm going to skip 3 because 3 is not a factor of 8. So I would go to 4 next. Do you guys get the idea? And I've already gone through 4 of them, and just took me a couple seconds. So there's 4 more before I realize, oh no, I got to do fractions. And the actual answer is 2/3. So I'm not going to spend all the time watching you sit here and make you go watch me do this, because that's just too tedious. But this is the method that you would go through. And you would finally get 2/3 as your root or your 0. So remember, it's factors of the constant over factors of the leading coefficient. Okay, let me walk through with different numbers. We have this polynomial, and we want to find the rational roots. Again, this time we're going to find more than 1. So let me walk through it again. We're going to start with 15. And remember, we are looking for factors of 2 over factors of 15. So we have lots of possibilities. But really, using synthetic division, we only have to find 1. And let me show you why that's the case. All right, so we're going to start with 1, our first factor of 1. And this is 15, and when we add, that's 17, and that's 17, and that's 20, and that's not going to work. So I'm just going to stop and erase and make this -1, see if we get a different result. So this is -15, -47, I add, I multiply, 47, 50, no way. So -1 doesn't work. Let's try for 2 and hope that it's a whole number. So change this to 2. And this is 30, -2, -4, -1, -2. Yay! We found our first root, or our first 0. It is 2. I'm going to circle it. Now what I have left, because this was x cubed, I've basically divided out one of those x's. This represents x squared. So at this point, I have 2 choices. I'm going to see if I can factor this. If I can factor it, that's so much easier. If not, I can use the quadratic formula to find the other 2 zeros. They're looking for rational roots, so if I get something irrational, then I don't have to keep going. I can stop. Irrational or imaginary. They only want rational numbers. So I multiply 15 times -1, I get -15, and there are factors of -15 that add up to -2. That would be 5 and 3. So I'm going to go ahead and rewrite this. I'm going to split this up. 15x squared minus 5x plus 3x minus 1. Just to review, factoring these, I'm going to walk through it. Divide out the 5x, and we get 3x minus 1. And I'm going to factor out a positive 1, and we get 3x minus 1. So my 2 factors are 5x plus 1, that's here, and the other one is 3x minus 1. There's our other factor. There's our 2 factors. Now from those factors, we can come up with our zeros. So if I set this equal to 0, 5x plus 1 equals 0, then 5x equals negative 1, x equals negative 1/5, there's one of my zeros. And basically, it's this number sign changed over that, so the other one is positive 1/3. And then 2, and there are my 3 zeros. So it's just finding the first one. Once you find that first one, boom, you're good to go, if it's only a cubic. If it's a quartic or a quintic, then you might have to find 2 till you get down to x squared. It's just the way it is, you guys. This is why you're going to love synthetic division so much. I really want to practice that more with you guys, but at the same time, I have more to cover in this section. So I'm just going to trust that you guys can walk through that and find those rational roots by using that method, and just contact me if you have any help, but you need to practice it on your own. Let's move on to the next thing. Okay, I want to talk to you about something called the conjugate root theorem, which basically says a lot of these roots or a lot of these zeros come in pairs. And when you look at the quadratic formula, you can see why that would be. Rational roots don't, because those are just nice, easy factors. They're just single numbers. They're what we have been finding. But once we get to down to a quadratic where we have to use the quadratic formula to find the last two, usually the last two zeros or last two roots, we have this plus or minus inside of this theorem, which means our answers will come in pairs. We will have negative b plus this and negative b minus that. And so when we simplify, if we have an irrational or if we have an imaginary, they're going to be conjugate pairs, one positive and one negative. For example, let's say I tell you that one polynomial has a square root of 2 as a root. Well, then you know this simplified to be a 2, and it was a positive square root of 2, so what else must that have been? A negative square root of 2. They always come in pairs. So they don't even tell you there's a negative square root of 2 because they know that you are smart and they know you know they all come in pairs. So there's also a negative square root of 2. That's the conjugate root theorem, that these things come in pairs. If this simplified to be 1 plus I, then you know, because of this plus or minus, that its partner must be 1 minus I. That's what it means by they always come in conjugate pairs. So 1 plus I and 1 minus I would both be zeros. So let's say you are given this problem. A cubic polynomial has these following zeros: 3 minus 2i and 5 over 2. What is the other zero? So no conjugate roots. 5 over 2 doesn't have a partner, but this one does. If 3 plus 2i is a root or a zero, then the other one must be 3 plus 2i. Did I misspeak earlier and say 3 plus instead of 3 minus? Back in my brain. Anyway, these come in pairs. 3 minus 2i would also have to have a 3 plus 2i, and then there are your 3 roots. That's all you have to do when they ask for that. Just provide the one that they're missing. Now we can take it a step further. Once you know how to find all the roots, now you should then be able to come up with the polynomials, and that's the next step. So let's say the problem now is what's the cubic polynomial that has a roots of -4 and 2i? So first you have to find the other third zero that's missing. If it has positive 2i, it's negative 2i. Now those are your zeros. From your zeros, you need to come up with your factors. So we're going backwards. If I have a zero of -4, its factor would be x plus 4, right? That has a -4 zero. X minus the zeros are the factors. So this is x minus a -4. X minus 2i is this one's factor, and x minus a -2i is this one's factor. So x minus the root or minus the 0 is the factors. Now that I have the factors, I multiply them together to get the polynomial. Always, always, always multiply these partners first. These are conjugates, so it'll be so much simpler. We've multiplied conjugates before, so that's what you want to start with for sure. So when we multiply this out, we end up with x squared minus 4i squared, or x squared plus 4. Since x squared plus 4 is a binomial, we can just FOIL that with this factor of x plus 4, and we should end up with our cubic. So this is x cubed plus 4x squared plus 4x plus 4. Wow. And there's our cubic. That's how we would do it. Candy. Okay, here is where this gets hard. I ain't gonna lie. This is where it gets hard. We want to know what quartic polynomial has these roots. 2 minus 3i, 8, and 2. Actually, I didn't need to put that in parentheses, but it has the roots 2 minus 3i, 8, and 2. What is the quartic polynomial? So from the zeros, I need to come up with the factors, but first I'm missing one. It's a quartic, I only have 3. The fourth one is this conjugate of this. If this is 2 minus 3i, it also has a 0 of 2 plus 3i. Now I need to come up with my factors. And remember I told you the factors are x minus my 0. So you might be going, oh my goodness, are you kidding me? So here's how this looks. X minus 2 plus 3i, x minus 2 minus 3i, and these two are easy, x minus 8, x minus 2. I'm going to ignore the easy ones. Let's deal with these, okay? So basically, I'm going to distribute this, and so I end up with x minus 2 minus 3i, and x minus 2 plus 3i. And there we go. Now, here are my factors. I've got to FOIL these. Believe it or not, you can FOIL them. Here's the secret to doing it. You have to treat this x minus 2 as one term, okay? X minus 2 and x minus 2. So now when I FOIL this, I do my first two, I get x minus 2 times x minus 2, which is x minus 2 squared, right? Then x minus 2 times positive 3i, and then x minus 2 times negative 3i. Because these are conjugates, what happens to those? Poof, all right? They disappear. X minus 2, that's positive, I'll show you, positive 3i x minus 2, and negative 3i x minus 2, oops, x minus 2, they cancel each other out, all right? So those disappear. So we have the x minus 2 squared, and now we have a negative 3i times positive 3i, which is negative 9i squared, or plus 9. Go ahead and FOIL x minus 2. That FOILs to be x squared minus 4x plus 4. And then we have that plus 9, so combine like terms. And that becomes plus 13. And we did it. We did it. So this would have been the quadratic that would have gone into the quadratic formula and gotten this kind of answer from the quadratic formula. And now we went backwards back to the quadratic that first originated it, which is pretty mind-boggling when you think about it. So now I have this quadratic. I'm going to go ahead and FOIL my other two factors. So this is x squared minus 10x plus 16. And now what I'm going to do is I'm going to multiply those two together for my final answer. You're going to do this just like you did multiplication in elementary school. So 13 times 16, I think that's 208. So it's positive 208. And this is negative 130x. And this is positive 13x squared. Now I'll multiply all of these by negative 4x. Let me see, 32, negative 64x, positive 40x squared, and negative 4x cubed. Now I'll multiply all of these times x squared. So 16x squared, negative 10x cubed, and x to the fourth. And now I add all my columns straight down. So I have x to the fourth minus 14x cubed, and these are all positive, aren't they? 4, 5, 6, positive 69x squared, negative 194x plus 208, and you're probably thinking, she's got to be kidding me. I'm not. There it is. You just did it. From those 3 zeros that they originally gave us, we were able to figure out what the quartic was, and that's how you do it. The textbook doesn't offer a whole lot of other practice in how to come up with these factors and how to FOIL them. A lot of practice would be helpful, but there's not a lot at the beginning of this, so hopefully there's more in the lesson. And I'll be happy to walk through it with you in class. There is still one more thing to go over in this section. Okay, the last thing I want to show you is Descartes' rule of signs. I want to remind you that, the days of graphing calculators are very, very recent. People have been doing this kind of math for hundreds of years, and everything was by hand. So when they were trying to put these together and take these apart, they would use every trick that they could come up with to make their job easier so that they didn't have to hunt and peck so much. And Descartes came up with this. When he had this kind of a polynomial like this, he would wonder, well, how many zeros are there really, and what are they like? But only real zeros, not imaginary ones, just real zeros. And how many of them would be positive and how many of them would be negative? He found this pattern that's consistent and works, and so we teach it to you now. And from it, he could determine how many positive real solutions this polynomial could have and how many negative real solutions this polynomial could have. All right, could have. Because this is an x cubed, there's just 3 altogether, 3 zeros, 3 solutions. They could be positive, they could be negative, they could be imaginary. But he noticed this pattern with the signs. And so here's what I'm going to show you. If you start at the beginning, what he did is he counted how many times the signs changed. So we started with positive, the next term's negative, that's the first sign change. Then it changed to positive, second sign change, and now we're done. So it has 2 sign changes. So this polynomial could have 2 positive solutions or zeros. But it also could have 0, because you take the number you get by counting the sign changes, and it's take that number minus 2, minus 2, minus 2. So in other words, if it was a super long polynomial and it had 6 sign changes, then your possibilities are 6, 4, 2, or 0. We're not going to do anything that big. This had 2 sign changes, so therefore it could have 2 or 0 positive solutions. Can't have 3, can't have 1. Either 2 or 0 positive solutions. Now, how do you count the negative solutions? So to count the negative solutions, instead of counting f of x, he counts f of negative x. So in other words, he made the x's negative, all right? So if I have an x to the 3rd power and I've made it a negative, it will become a negative, because negative times a negative times a negative, this will become a negative x cubed minus an x squared. So it'd be like this. Okay, do you see how I just made the x itself negative? But a negative x times a negative x goes back to positive, and so we're still subtracting x squared. So this sign didn't change. It stayed a negative. This term doesn't have an x at all, so it doesn't change. So when you basically, the summary kind of thing to think about is when you're negativizing, that's my made up word, it's not real, but I got it from a student. That's Zoe's word, negativizing, so give Zoe credit. When you negativize the x, it will change the sign of any term that has an odd power, odd degree. So it'll change third x to the thirds, x to the fifths, or single x's. But because a negative times a negative would still be positive, it does not change x to the squared or x to the fourth. It doesn't change even degrees, just the odds. So now let's count the sign changes. It starts as negative, sign didn't change, it only has one sign change. So that means for negative is just 1. Now I can't take 2 away from 1. Negative 1 wouldn't make any sense. That's my only possibility. So now I know for sure there is one negative real 0. So if I was hunting and pecking like I did earlier and using synthetic division, I would try my negatives first because I know for sure I've got one negative. Do you see how that would work? And plus I'm only looking for factors of 1. So probably negative 1 is a 0. 2 and 1 would make my 3. If it's 0 and 1, how would I get to 3? It is possible then I could, if this was 0, then I would have 2 imaginary. Your textbook doesn't ask you to list positive, negative, or imaginary possibilities, but I think you should. So you have to account for 3. So it's either 2 positive and 1 negative, or it's 0 positive, 1 negative, and 2 imaginary would be your zeros in this polynomial right here. Okay, your text only asks for the real roots, the possibilities of real roots, but I don't still like throwing in the imaginary in there. If I have this polynomial, this quartic, what does Descartes' rule of signs tell us about the possible number of real zeros, positive real zeros, and negative real zeros? So let's walk through it again. To find the positives, I don't change anything. I just take the original polynomial as it is and I count the sign changes. So it started with positive, went to negative, there's 1. Switched to positive, there's 2. Went to negative, there's 3. So positive, I got 3. So it could be 3 or, do you remember? 1. Okay, now let's check the negative. So when I negativize my x's, so I'm going to change all of these to a negative, this, because it's to the 4th power, won't change. This will, and I'll be subtracting a negative x cubed, so that will change to a positive x cubed. This, because it's squared, will go back to positive, so that doesn't change. And this has no x, so there we go. So now let's count our negatives. So we start with positive, positive, positive. Oh, only 1 sign change. So there's 1 negative. And there we go. So we could have 3 positive and 1 negative, or 1 positive and 1 negative. And if we have 1 positive or 1 negative, then we would have 2 imaginary because we need 4 altogether. If you have a graphing calculator, you could put this in and then confirm what you have. If you have 3 and 1 or 1 and 1 with 2 imaginaries. The graphing wouldn't give you the imaginaries, but you can just look for the x-intercepts. How many times does your graph go through the x-intercept or touch it and come back? That would be your zeros. Okay, your lesson check question for today, I have this polynomial up here. I'm going to go back to what we learned at the beginning of this video and say, what is a list of all the possible roots for this polynomial? So what, in other words, if you were going to set up synthetic division, what numbers could possibly work? Positive and negative, list them all out for me. And it'd be easier if you put it all in parentheses and then put plus or minus to the left and all the possibilities. I hope you remember that's all the way back in the beginning of this video. So that's your lesson check. And yeah, have fun with this, and I'll see you guys next time.